Good afternoon. Today we are going to discuss few of the most important applications of mathematics in physics. Mathematics by definition deals with numbers, their interpretations and their applications to form sets and groups for different systems. In fact, mathematics is the link between nature and us, the human beings, as it is only through numbers our brains can comprehend the world around us. Of all the sciences, physics is the most encompassing as it reveals the structure and beauty of nature from microcosm to macrocosm through the language of mathematics. Though physics is basically an experimental science, the understanding and interpretations of all observations have to be in terms of mathematical models that makes the science relevant to the day-to-day happenings and make us realize the cause and effect relations. In fact, the search for understanding the universe vis-a-vis the world around through those started more than 500 years ago, what we call physics today got its real foundations only with Galileo in the 16th century and got its structure from Isaac Newton in the 17th century. In fact, it is well known that Newton propounded the laws of motion. Before him, for centuries, philosophers and thinkers, starting from Pythagoras, Plato, Aristotle, followed by Ptolemy and Euclid, had tried to evolve systems of description for explaining the movement of celestial objects, which were more philosophical rather than scientific. With Copernicus, a revolution set in, as the heliocentric description of planetary system sounded more logical, which then got further strengthened by the meticulous observations of Tycho Brahe, Kepler's enunciation of laws of planetary motion around the sun. It is in this period that Galileo Galilei gave the concept of inertia and the ensuing principle of relativity, which is stated as follows. The mechanical laws of physics are the same for every observer moving uniformly with constant speed in a straight line. Newton later formulated this principle called the law of inertia as the first of his three laws of motion. Motion, by definition, is simply the description of change of position with respect to time, and position, as everybody knows, is simply location in space. Thus, Newton realized that describing motion requires the identification of position in space at various times. For this, one needs geometry and systems of coordinates, which define the position of objects with respect to a reference system or origin. This triggered the notion of applying the Euclidean geometry in 3 dimensions, as space was of 3 dimensions. The concepts of infinitesimals were brought in and the discipline of calculus emerged. Newton's first law, as you all know, states every body continues in its state of rest or of uniform motion unless it is compelled to change by an external agency. In order to understand this, let us set up a frame of reference which, according to the Euclidean geometry, can be given by a Cartesian system x, y, z. If the body is at the point P at rest, then obviously it is described in this system by dx, dy, dz all zeros because there is no displacement of the particle in this system. This is true for all t. On the other hand, if it is moving with a constant velocity, then one will have dx upon dt v1, dy upon dt as v2, dz upon dt as v3. It's again true for all t. Now v1, v2 and v3 are the components of the velocity in the three directions. It is simple to see that differentiating these equations with respect to time gives d squared x by dt squared equal to 0 and the two other equations as shown here. And as v1 and v2 and v3 are the same for all t, the derivatives with respect to t is 0. Thus we find the first law of Newton expressed in mathematical terms says that acceleration of the particle is 0 unless it is acted upon by an external agency. Newton's second law states that the external agency is defined as the force, and it is proportional to the acceleration that the body acquires under its influence. Mathematically, it can be expressed as F proportional to E or F equal to ma, where m is the mass of the body. According to its definition, the acceleration is given by the three components ax, ay and az as shown in the picture here. And so now, by Galilean relativity, these laws must be the same for all inertial observers. As the time t is the same for all observers, when we choose different frames of references for different observers, only the spatial coordinates would change. Let us consider two observers, O with the system x, y and z, O prime with the system x prime, y prime and z prime, such that P has the velocity v1, v2, v3 with respect to O, and v1 prime, v2 prime, v3 prime with respect to O prime along the three directions x, y and z. Now, expressing the first law mathematically, we have the two sets of equations ax equal to 0, ay equal to 0 and az equal to 0 in the frame O, and ax prime, ay prime and az prime 0 in the other frame. So, expressed in terms of x and t, these are simply the second derivatives are 0. Now, all we can do is integrate these equations. It's just a simple second order equations, which when you integrate, once you get dx by dt, dy by dt, dz by dt as constants, v1, v2, v3, and similarly dx prime by dt, dy prime by dt, dz prime by dt is v3 prime, etc. Now integrating again the first order equations, you get simply x equal to v1 t plus a1, y equal to v2 t plus a2, z equal to v3 t plus a3, and similarly in the other frame. So with this now, it's very simple. As t is same for both observers, you can simply subtract x prime minus x, y prime minus y, z prime minus z, and accordingly get v1 prime minus v1 of t, v1 minus a1, these simple equations. It is clear that v prime minus v gives the relative velocity of O prime with respect to O, because v is the velocity of the particle in O, p prime is the velocity in O prime. The difference between the two gives the relative velocity between O prime and O. Supposing you call it as u, then you get the relation between the two sets of coordinates to be as given by this. Let us now consider the case of a particle under constant acceleration. Say a along the direction x. By definition, we have d squared x by dt squared is a, which on integration gives dx by dt is at plus u, and on further integration yields x equal to at squared by 2 plus ut plus c. Now, if a particle having an initial velocity u at t equal to 0 start from the origin and is subjected to a constant acceleration a, its final velocity v after reaching a distance s is given by v will be u plus at, and the distance travelled s is ut plus half at squared. Now these two equations you can simplify to get the third equation between v and u and s, which is v squared equal to u squared plus 2as. Having gotten these three equations, we now know that these are the three equations which form the basis for the entire Newtonian mechanics. The first thing one notices here is that if there is no force acting, then as acceleration would be 0, the equation for the path is a straight line, whereas the force or acceleration induces a curved path. That's because we saw that we had a linear equation when the velocity was uniform or the acceleration was 0, and on the other hand, when acceleration was non-zero, we had a second order quadratic equation, and that induces a curved path. The best illustration of this is something known to every child, that a stone thrown upwards and away falls back in a curved path. The trajectory of a projectile is a parabola. Now, the important link this brings from the analytical geometry point of view is that a linear equation represents a straight line trajectory, whereas a nonlinear equation like quadratic and higher degree represents a curved trajectory. While Newton formulated the laws of motion, he was also pondering over the fact that planets move around the sun in curved paths, as depicted from the works of Tycho Brahe and Kepler, which indicated that there must be a hidden force deviating the planets from the straight line trajectory and acting towards the sun. Now, let us see. Our next step would be to consider the motion of a particle in a circular path and find the corresponding mathematical equation which describes the required physics. Let us now consider the motion of the particle along a circle. Now, let us this one. According to Galileo, when the particle is at P, when it moves, it should go according to Galileo in this line PB here. But actually, since it is a circular motion, the particle, instead of going to B, it's going to A. Therefore, this says that as the particle is moving along this, that means that there is a force pulling this particle down towards O, which such that the distance BA here, BA is A dt squared. This is according to what we just derived now. S is equal to half A t squared formula, that is the one. And now this one, so once you have this, from the triangle OPB, BP squared is equal to OB squared minus OP squared. Simple Pythagoras theorem. Now, OB squared minus OP squared can be written as OB plus OP into OB minus OP. Now, OB plus OP, OP is same as OC, the radius of the circle. That becomes BC. And OB minus OP becomes AB. And now, BC into AB, BC can be written as AB plus AC or CA. Therefore, BC is AB plus AC into AB. Therefore, BP squared becomes AB squared plus 2R, because if R is the radius of the circle, this is the diameter, AC. Therefore, 2 times R into AB. Let us call it equation 1. Now, from the triangle ABP, BP squared is AB squared plus AP squared. Now, using 1 and 2, we get PA squared is twice R into AB. Our AB is A dt squared. Therefore, PA squared becomes twice of R into A dt squared. Now, let us say T is the time period of the particle. Then one has the time taken by the particle to go from the position P to A, PA, and divide by the time taken dt, that should be 2 2 pi r, which will be this radius of the circle, since the period represents the time taken by the particle to complete the circle. Therefore, Pa by dt is equal to 2 pi r by t. Now, 3 and 4, one thus gets 2r into a is 4 pi squared r squared by t squared, or a is 2 pi squared r by t squared. Now, luckily, Newton was familiar with Kepler's laws, and Kepler's third law says that the square of the periods of the particle, planets, is proportional to the cube of the radius vector of the orbit. Therefore, t squared should be proportional to r cube. Now, put this here in this equation. All you get is a proportional to 2 pi squared r by r cube, which is 1 upon r squared. This is the famous inverse square law. So, now the Newton's third law of motion comes into picture. See how very simple things, all the equations which we have already seen are being used here, and with simple geometrical concepts of Pythagoras and certain algebraic relations. Using them, you got the relation that the force is proportional to 1 upon r squared. The most important thing now is, according to Newton, there were 3 laws of motion. One was, of course, law of inertia. Second is the definition of force. And third was such that action and reaction are equal and opposite. Therefore, if there is something sitting in the center, pulling the particle towards it with a certain force, by the third law of Newton, this must be exerting the same force on the particle the other way. Now, if m is the big mass of the big body and m is the mass of the particle, therefore, you get between the two bodies there must be a force which is proportional to 2 masses divided by r squared. Or